Last time we proved the version of the fundamental theorem of calculus that's easy to prove, that follows from the definition. Now let's rephrase this in terms of what you are probably used to thinking of as the fundamental theorem of calculus. Let's let f be a continuous function on the closed interval from a to b. So f is a function from a to b to the real numbers, is continuous everywhere on AB. F is continuous at x for x at interval. And let's let big F be a C1 function. And what that means is that f is a function from a to b, defined on a to b and mapping into the real numbers. F is differentiable everywhere in this real numbers, and f prime is a continuous function. And let's suppose further that f prime is equal to little f, that is, f prime of x is little f of x for all x in our interval from a to b. And the conclusion is that the integral from a to b of little f, that's equal to big F of b minus big F of a. So let's prove this. So we're going to define g of x to be the integral from a to x of f. And then by the fundamental theorem of calculus, that is by theorem 3.2.1, g is continuous on the interval from a to b. And since little f is continuous everywhere, g prime of x equals f of x. So exists and is continuous for all x in AB. All right, now let's let h of x be big G of x by minus big F of x. Then h is continuous on AB because big G and big F both are by assumption. H prime equals 0 on the closed interval, but as it happens, we only really need the open interval. So by corollary 2.3.6, we have that h is constant. So let's write this. Integral from a to b of f. That's big G of b. That is also big F of b plus big H of b plus H of b. just by definition move the f of x over in the definition of h of x. That's f of b plus h of a, because h is constant. That's f of b plus big G of a minus big F of a, because that's the definition of h of a. That's f of b minus f of a, which is what we want, plus the integral from a to a little f, which by definition is 0. So that is f of b minus f of a. In practice, this corollary is how everybody wants to evaluate an integral. So, for example, if I asked you to find the integral from 3 to 5 of x cubed dx of a function f where f of x is, let's say, x cubed, then your solution, which you all, I'm sure, remember from calculus, is you just let big F of x be 1/4 x to the 4th. Then the integral from 3 to 5 of little f, big F of 5 minus big F of 3 is 5 to the 4th, which is 625 over 4, minus 3 to the 4th, which is 81 over 4. And so that's how everybody wants to solve integrals. I should point out that the Riemann definition, one, we like it as mathematicians because it's a lot more precise, it's easier to get your hands on, but also there are some functions you just can't integrate using the fundamental theorem of calculus, so even the engineers have to deal with Riemann some way. So for example, this is a classic example of a function whose integral everybody cares about. It shows up in statistics all the time, but it has no closed form. So we cannot find an elementary function. That means a function written in terms of, powers, square roots, exponentials, logarithms, sines, cosines. We can't find a function in terms of the functions you know and love with the right derivative. So the best we can do is to compute, or rather have a calculator compute, the Lebesgue sums, the Darboux sums for finer and finer partitions. And notice that this is, in fact, a decreasing function, at least on the interval from 0 to 1. So this is indeed the upper sum and the lower sum of f. and make sure we find some partition that forces those close to each other. And that's sort of the best we or even the engineers can manage. That's not to say that an antiderivative of our function e to the minus pi x squared doesn't exist. So let's let f be a Riemann integrable function. So all continuous functions are Riemann integrable, so all continuous functions we can do this for. And then you can define a big F of x as the integral from a to x little f. We call big F the indefinite integral. Of little f. And then if f is little f is continuous by the fundamental theorem of calculus, big F prime equals little f. So if you've got a continuous function, it has an antiderivative. It's the same as the indefinite integral. It's just that you may not be able to write it in terms of any functions you know and love. If you need an actual numerical value, the best you can do is approximate it on your calculator using Darboux sums, but that's okay. If you want something like a sine or an exponential or a logarithm or even a square root, even the square root of 2, if you want an actual number, you have to approximate it. Let's check and make sure that a couple of the formulas you know and love from Calculus 1 work. So here's theorem 3.2.5. This is the change of variables. Also known as U substitution. So let's call it U be a C1 function, so one continuous derivative on an interval from A to B. And then U of AB, that is the image of AB under U, is a subset of I where I is let's say an interval. And extreme value theorem, you can insist on I being a bounded interval, but we don't care about that too much. Let f be a continuous function on I. So f doesn't have to be differentiable, but f is a function that's defined everywhere on I, and that is continuous. And then integral from A to B, f composed with U times U prime, that is equal to the integral from U of A up to U of B, and then there is f. And the proof is not too tricky. Let's let big F be the antiderivative of little f. Then then the integral from u of a to u of b, yes, I suppose here, big F, I cannot start at a, I have to start at u of a, little f, that's big F of u of b minus big F of u of a. In this particular case, that's 0, but let's keep it. Now let's let G be big F composed with u, and then G prime of x is big F prime of G of x times G prime of x. So, and we remember that big F prime is just little f. Sorry, that is, sorry, I've been saying G, that's supposed to be a U there. So the integral from a to b of f composed with u times u prime, that's the integral of g, so that's g of b minus g of a, which is big F of u of b minus big F of u of a, which we saw, which is showing up there, is exactly what it's supposed to be. So that completes the proof. And let's also check integration by parts. Let's let f and g are both C1 functions on a and b. That is, f and g, they're both continuous, they're also differentiable, and their derivative has to be continuous. So then here's how you write integration by parts for definite integrals. Integral from a to b of f prime g, that's f of b g of b minus f of a g of a, and then you have to subtract from that the integral from a to b f g prime. And again, this falls straight out of the fundamental theorem of calculus. Let's let big F of x be f of x g of x. So f prime, so big F prime of x, we've proved the product rule back in chapter 2. So let's just write that down. Then integral from a to b f prime g plus f g prime. That's the integral from a to b big F prime. That's big F of b minus big F of a. F of b g of b minus F of a g of a. And then our integral, remember by linearity of integrals, this is equal to the integral from a to b f g prime, and then plus the integral from a to b f prime g. And then all you have to do is move this term over to the other side, and that completes the proof. In this section, we are finally going to define logarithm and exponential functions. We've sort of defined exponential functions. We've defined what it means to raise a number to an integer power or to a fractional power that in terms of square roots, which are the inverse functions to the integer powers. But now we'll talk about how to raise a number to an arbitrary power, how to get the full force of exponential and logarithmic functions. So here's the first thing we need. Here is how we are going to define the logarithm. We will define the logarithm and use it to construct the exponential function. You're probably used to doing it the other way around, but if you want to be really rigorous and solid, it's a little easier this way. So let's let x be a positive real number, and we define the logarithm of x. If you want to connect this up with your high school definitions, this is the natural log of x, not the log base 10 of x. If you're a mathematician, natural logarithms are sort of like radians. They're really the good way to do things. This is the integral from 1 to x of 1 over t dt. And notice the function 1 over t, that is continuous on the open interval from 0 to infinity. It's not continuous at 0, so we can't integrate it across 0, but it is continuous on the interval from 1 to x, or from x to 1 if x happens to be less than 1 but bigger than 0. So we can define this integral. It's a meaningful thing in terms of Riemann sums. All right, so the first theorem we have to prove is that all the properties of logarithms that we know and love are still true. So first thing we're going to write down is that log is differentiable everywhere for all x between 0 and infinity, and log prime of x, that's the derivative of the logarithm, is 1 over x. And this isn't hard to prove. This falls straight out of the fundamental theorem of calculus. Next part is logarithm of 1 is 0. That's again true by definition. Logarithm of x is positive if x is greater than 1. And log x is negative if x is less than 1, and let's emphasize that x is positive just to be sure the logarithm is defined. All right, then everybody's favorite property of logarithms. If a and b are both positive, then logarithm of a times b is log of a plus the log of b, and the logarithm of a over b is log a minus log b. And I'll point out by induction if n is a natural number, then logarithm of a to the n, that's log a times a times a n times, that's n times the logarithm of a. And then the last thing to notice is that log is strictly increasing on the interval from 0 to infinity and is a bijection from 0 to infinity into the set of all real numbers. Then proof. Part A, this follows immediately from theorem 3.2.1, that is the fundamental theorem of calculus, yields this result immediately. Also, just go back to the last video and look up what the fundamental theorem of calculus said. Right. Then part B, I'm going to write down that log 1, that's the integral from 1 to 1 over t dt, is 0 by definition. And we could try to prove the greater than and the less than conditions, but I think I'll wait and prove that in part after we've proven part D. Once we've established that the logarithm is strictly increasing, the rest of part B will follow. Now let's prove part C, because we'll need it to prove part D. So here's the simplest way. F of x is logarithm of ax minus logarithm of a minus the logarithm of x. So we are fixing a and letting f of x be defined like this. Then f prime of x, by the chain rule, we get 1 over ax times the derivative of ax, which is a. Then log a is, we fixed a, so that's a constant, so that's 0. Then we subtract 1 over x, simplifies down to 0. So f is constant on the interval from 0 to infinity, and that is true by proposition 2.3.7. Sorry, corollary 2.3.6. So f of b so here's f of b. It's equal to f of a. It's equal to f of 1 because f is constant, which is log a minus log 1, which we said was 0 minus log a. One of those is a log 1a, but that's just the same thing as log 1. Anyway, log 1 is 0, so this is just log a minus log a is 0. Then we write down what f of b is. That's log ab minus log a minus log b. And then rearranging, so log ab is log a plus log b. And then a over b and b are both positive numbers, so logarithm of a is logarithm of a over b times b is log a over b times log b. So plus log b, multiplication inside of a logarithm turns into addition outside. So log a over b just a little bit of algebra, log A minus log B. Now let's prove part D. So log prime, that's 1 over t, that is positive on 0 infinity. So log is strictly increasing on 0 infinity, and that's true by proposition 2.3.7b. And so this yields the remainder of part C of part B, that is log x is strictly greater than log 1, which is 0. If x is greater than 1, log x is less than log 1, which is 0. If x is less than 1, so C holds. Let's go ahead and name the two parts of item B, B1 and B2, because because we're proving them separately. And similarly, we'll name the two parts of part D, part D1 and D2. So now let's think about part D2. So log is strictly increasing. That was part D1. So log is injective, 1-to-1. And clearly, logarithm, its domain is the positive numbers and its range is the real numbers, and we need only show log is surjective from the positive numbers to the real numbers. So let's prove the logarithm is surjective, and we're going to do this. We're going to pick a real number a, and we're going to prove that a is the logarithm of something. And how we do this, we're going to notice that the logarithm of 2, which is my favorite number, is strictly greater than the logarithm of 1, which is 0. So by the Archimedean property, that is proposition 1.2.6 in your book, there is, or rather there are integers n and m, some natural numbers, with a being between n times the logarithm of 2 and negative m times the logarithm of 2. And then we can write, and then n times the logarithm of 2, that's the logarithm of 2 to the n, which is a positive number, and which is the logarithm of a positive number, in fact, an integer. And then minus m times the logarithm of 2, that we can write that as log 1 minus log 2 to the m. And so that's just the logarithm of 1 over 2 to the m. Then, so by proposition 2.2.4 because the logarithm is differentiable, or fundamental theorem of calculus, logarithm is continuous on, let's say, interval from 1 over 2 to the m up to the 2 to the n. So by the intermediate value theorem, there is a t in this interval with logarithm of t equal to a. Thus, the logarithm is surjective. From the positive numbers to the real numbers. So that completes the proof. That shows that the logarithm is bijection. This section is all about defining the exponential and logarithm functions that we know and love. So let's just put down all those definitions in terms of the log function we've just defined. And then basically the rest of section 3.3 is checking that the log and exponential functions that we've just defined, the power functions, they all have the same nice properties that we expect them to have. So definition 3.3.3. Remember, we've seen that the logarithm is a bijection whose domain is the positive real numbers and whose image is all the real numbers. So we define exp. That's a function from the real numbers into the positive real numbers, is the inverse of the logarithm. So the function exp is the inverse of the logarithm. So we're used to defining logarithm as the inverse of the exponential function, but in this case it's easier to define it the other way. Here's our next definition. E is the exp of 1. So that number that you probably know, 2.71828, it's defined precisely as the exp of 1. And log is, we're going to discover, is log base E. Exp is, we'll see, e to the power of. So here's how we define logarithms with other bases and power and arbitrary powers. So let's let x be a positive real number and a positive or negative real number. Then, all right, we know how to take x to the power of an integer. That's repeated multiplication. We know how to take x to the power of a fraction that involves nth roots, that involves inverse functions to integer powers. We know how to deal with negative integer powers, or power of negative 1 is divided by, but we don't really have a definition of a real number to the power of a real number, not a fraction. We can't write an expression for x to the a in terms of, fractions in terms of roots. So we define that to be exp of a times log x. And finally, logarithms to other powers. Let's let b be positive, b is not allowed to be equal to 1, and x is positive, x is allowed to be equal to 1. Then the logarithm to the base b of x, that is defined to be the logarithm of x divided by the logarithm of b. So those are our definitions, and now let's see that they satisfy all the properties we need them to do. A lot of these are going to be just kind of tedious to check, so some of them will be left to homework or the exam problems, but let's check a couple of these. So this theorem is properties of the exp function. So here's our first property, is that exp is a continuous function with a continuous derivative, and exp prime is exp, which of course means that x is a continuous function with infinitely many derivatives. You can keep differentiating, but you'll only be asked to prove that it has one derivative. Exp of 0 is 1. Exp of x is greater than 1 if x is positive, and exp of x is less than 1 but is positive if x is negative. All right. Third part is that exponentials of sums are what you expect them to be products. X minus a is 1 over exp a. And so exp of NA is exp a to the n for all natural numbers n. You get that from the above by induction, and these are true if a and b are any real numbers. Part D is that exp, its domain is the real numbers, its image is the positive real numbers. That is a strictly increasing bijection. And parts A through D, really they follow immediately from the fact that exp is the inverse to the logarithm. You prove theorem 3.3.4 from theorem 3.3.2. The only new part of theorem 3.3.4, and the one I'm going to prove for you, is the following. Is the limits at plus or minus infinity. And I will finish this video just by proving part E. So let's remember that limits as you go to infinity involve numbers being bigger than other big numbers. So we'll direct our reader to pick a positive number k. Since exp is surjective, we have that there is a p in the real numbers such that exp of p equals k. And then if x is bigger than p, then by part D, because exp is strictly increasing, exp of x is bigger than exp of p, also known as k. And then all the stuff in green is precisely the definition of the limit as x goes to infinity, exp of x equals infinity. And we can do exactly the same thing for the other limit. We pick a positive number epsilon, and then there is a real number r with exp of r equaling epsilon. This is again, and because exp is surjective, so if x is less than r, then exp of x is strictly less than exp of r, better known as epsilon, and 0 is less than exp of x, because exp of everything is positive. Since the domain of x is the positive numbers, so the absolute value of exp of x minus 0, that's equal to exp of x, because exp of x is positive and 0 is 0, is strictly less than epsilon. And that is the definition of limit as x goes to minus infinity. This is definition 2.1.12.